Welcome back to the deep dive. Today we're going to be tackling something that I think looks super cool visually, and that is chevron folds.
Yeah, chevron folds are really interesting.
Yeah, so these are those really striking V shapes you see repeated sometimes in rock layers. And you guys send in some really fantastic material on this.
Yeah.
There is a scientific thesis, some Wikipedia entries, both the simple and the standard English ones, a YouTube video transcript from the Professional Geology Club, and a blog post from EGU blogs.
Great sources.
Yeah, really good stuff. So our goal is to kind of pull out, the essential information from all of this so you can really kind of wrap your head around, what these are, how they form, and why they're important for understanding, the planet, basically.
Absolutely. You're looking to get informed quickly and thoroughly, and we've got all these sources to help bring you those core insights.
Yeah, and speaking of, getting right to it, let's just jump right in.
Sounds good.
So what exactly is a chevron fold? Like when you see these, and definitely take a look online later, search Shutterstock or a EGU blog.
Yeah.
What are you actually seeing?
Well, the thing that really pops out about chevron folds is their regularity. You see this, series of folds that repeat so neatly and create that characteristic, V or zigzag shape. And the sides of those Vs, what we call limbs, are usually straight. And they meet at these really sharp bends, which are called hinge zones. And often these hinge angles can be really quite tight, like 60 degrees or less.
Yeah, it's a very defined, almost geometric pattern.
Yeah.
And the simple English Wikipedia says, regular folded beds with straight limbs and sharp hinges. And then it goes on to say that they form a set of V-shaped beds.
Exactly.
And it also notes that it's often just called, chevron folding.
Right.
So it seems like the repetition is key.
Yeah, the repetition is definitely a key feature. And as with any geologic structure, there's usually a primary force behind it.
Right. And in this case, it would be compression.
Exactly. It's this compressive stress. And it doesn't matter if it's from these large-scale tectonic plate movements or more localized pressures. That compression is the main driver of chevron folds. And the YouTube transcript from the Professional Geology Club, they actually do a great job of explaining how that squeezing force causes rocks to kind of bend and deform, which eventually leads to these, striking folds.
Okay, so pressure makes rocks bend. That's the fundamental push.
It is.
But why the sharp V in that consistent pattern?
Yeah.
That's where I think the idea of competence comes in.
Yeah, competence is key here.
Yeah.
So when we talk about competence in geology, what we mean is a rock layer's resistance to deformation. It's basically how strong that rock layer is.
Okay.
And to illustrate this, the EGU blogs post uses a great analogy, an ice cream sandwich.
Okay. I like where this is going.
So those harder biscuit layers, they're more competent. They tend to kind of snap if you bend them too much. But the softer cream filling in between, that's less competent. It'll flow more easily.
Right. That's a good way to think about it.
Yeah.
So how does that relate back to folds?
Well, chevron folds tend to form in places where you have these layers of rock with very different competencies stacked on top of each other. And both the simple English Wikipedia and the EGU blog actually mention turbidites as a really common example of this.
Yeah, turbidites.
Yeah, so turbidites are those deep sea deposits, and they often have these alternating layers of harder sandstone and softer shale.
Okay.
And that difference in strength really matters for forming chevron folds.
Right. So the tougher sandstone layers, those resist bending smoothly. And instead they kind of form those sharp angles. And then the softer shale layers kind of accommodate all that folding by just, deforming more easily.
That's a great way to put it. You got it. And to add to that, the Missouri S&T thesis, they point out that the friction between these different layers also plays a role. So in their models, they found that, if there's less friction, you can actually get chevron folds that have larger amplitudes. So taller Vs and sharper hinge angles, so those tighter bends.
Okay.
So it's not just about the difference in strength, but also how easily those layers can slip past each other.
Wow. So there's multiple things going on here.
Exactly.
Now, the standard Wikipedia entry talks about 4 stages in the development of these folds. Walk us through those.
Sure. So the first stage is what's called sinusoidal nucleation.
Okay.
And that's basically a kind of gentle, wavy bending of the rock layers. And then as that progresses, you get to concentric folding, where those bends become more pronounced.
Okay.
And then in the third stage, the limbs, so those are the sides of the wave, they actually start to straighten out, and the hinge areas become sharper. So that's where you really start to see that V shape emerge.
Okay.
And then finally, the chevron fold tightens. The angle between the limbs decreases even further.
And as that angle at the hinge gets super small, like close to 60 degrees, what happens in terms of like how the rock layers deform?
Well, it's really fascinating. At that point, the friction between the layers actually makes it harder for them to just, slide past each other or for the softer layers to just flow. So instead, the entire stack of rock tends to deform through what's called pure shear.
Okay.
So it's almost like if you, imagine squeezing a block of clay from all sides. That's more like pure shear, a kind of uniform compression and stretching compared to, that sliding motion of flexural slip, which we'll get to in a bit.
Okay.
And what's really interesting, the Wikipedia entry notes that, theoretically, there's no limit to how sharp that fold angle can get.
Wow.
It can just keep getting tighter and tighter.
That's cool. Okay, so we've got the shape, the compression, different rock strengths, and these stages of development. Now, the Missouri S&T thesis, it really goes deep into the idea of flexural slip. What exactly is that, and how does it relate to forming these chevron shapes?
Yeah, flexural slip. So that's a concept where as the layers hold, they actually slide past one another, almost like, pages in a book when you bend them.
Oh.
And the thesis mentions that some models actually propose this flexural slip as being essential for even initiating, the whole chevron folding process.
Yeah, okay.
And their own modeling shows that this sliding starts happening super early in the folding process when there is just a small amount of shortening of the layers. So you've got this movement going on at the layer level as well.
So that sounds like a pretty key mechanism, but I feel like I remember seeing that there's some debate about whether it's the only way they form.
Yeah, that's a good point. There are some other recent numerical studies, and these are, focusing on single layers, that suggest that flexural slip on its own might not be enough to create chevron folds. And these studies focus specifically on rock layers that have a certain kind of elasticity and viscosity. So again, highlighting the complexity of all this. It's not a simple process.
It's not as simple as it seems.
No.
And this is where the work by Wu at Missouri S&T really comes in, because they did all this computer modeling.
Yeah.
They changed a bunch of different factors to see what would happen. So what were some of the main things they kind of messed with in their models?
Well, they looked at a couple of key things. One was the initial shape of any kind of imperfections in the rock layers.
Okay.
So they either started with these smooth, wave-like bends, which they called sinusoidal perturbations.
Okay.
Or they started with more random, chaotic variations, kind of like white noise.
Gotcha.
And they also changed the wavelength, so that's the distance between those initial, bumps or wiggles, and they used different proportions of what they considered to be the typical folding wavelength. And then finally, they also played around with the amount of friction between the rock layers. So they tested both, high and low friction scenarios. And just to make sure they saw those fold shapes really develop, all their models had a pretty significant amount of overall shortening, around 60%.
Okay, so a huge range of conditions tested. What were some of the key results, in terms of getting those really nice symmetrical chevron folds that we all picture, when we think of these things?
Well, one of the most interesting findings was how much the outcome depended on those initial wrinkles. For the models that started with those smooth, wave-like bends, they only got those, textbook symmetrical chevron folds when the initial wavelength was pretty short, only about 10% of that dominant folding wavelength they were using.
Oh, wow.
So if those initial bends were longer, they tended to get more rounded circular folds or just wavy folds, not those sharp Vs.
Wow. So it's almost like a specific type of initial crinkle that's needed.
It is.
What about the role of friction in these models?
Yeah, so friction was really key. In the models with those smooth initial bends, if there was lower friction between the layers, the chevron folds ended up being taller, more pronounced with those, sharper angles at the hinges. So basically less resistance to sliding helped create that classic chevron look.
Okay. And what happened when they started with that more chaotic white noise pattern of initial imperfections?
So that actually led to some different results. With low friction, they saw these isolated and often asymmetrical chevron folds pop up. So not that neat, repeating pattern that we usually associate with chevrons.
Right.
And if there was high friction in those white noise models, it just tended to reproduce the dominant wavelength of folding without actually forming any clear chevron folds.
Right.
And what's even more interesting is that the amount of friction could even influence, what that dominant wavelength of folding ended up being in those white noise simulations.
The friction really changed things up.
Yeah.
Okay, so the big takeaway here is that flexural slip is probably happening, early on. But those tiny little initial conditions, like how crinkled the layers are to begin with, and, how easily the rocks slide past each other, are super important.
Right.
To determine whether you actually end up with those, like, textbook chevron folds.
You got it. And I think it just emphasizes how complex, these geological processes really are. You've got all these different factors kind of interacting and influencing each other.
Yeah, for sure. Now, as these folds form, especially at those, like, really sharp hinge points, doesn't that sometimes create, like, a void or open space?
It does.
So how does the rock, like, deal with that?
Right. Well, the standard Wikipedia entry, it actually highlights a few different ways that those rock layers accommodate that kind of, geometric challenge. Right. So things like saddle reef structures, where you have these minerals precipitating out and filling those open spaces, or hinge collapse, where the layers kind of, buckle inward, or just simple stretching, what we call dilation, of those less competent layers.
Okay.
They just kind of stretch out to fill the gap.
And the different types of rock within the fold, do they behave differently in these hinge zones?
They do, yeah. The Wikipedia entry points out that the more competent, stronger layers, they tend to fracture, often in this kind of radial pattern. And then later on, those fractures can get filled in with, like, crystalline veins.
Oh, wow.
Whereas the less competent, weaker layers, they deform in a more ductile way, meaning they kind of flow and change shape more easily. And they often develop these complex patterns of parallel fractures called cleavage.
Wow. So even within that, like, tight bend, you see this contrast in, like, how the strong and weak layers handle the stress.
You do. It's remarkable.
Now, we've talked a lot about the contrast in competence between rock layers, but what other factors play a role in whether, chevron folds actually develop?
Well, the standard Wikipedia entry mentions this. One really important factor for stability is the thickness of those more competent layers, like how consistent it is. If those stronger layers have a relatively uniform thickness, it helps the whole fold structure stay stable.
Okay.
And what's interesting is that the uniformity of the less competent layers, it doesn't seem to be as critical for stability.
That makes sense. It's like the stronger layers are providing the, like, framework.
Right. Exactly.
What about the actual size of the rock beds, like the thickness versus the length?
So that's definitely important too. There seems to be this general rule that a ratio of about 1 to 10 between the thickness of a competent bed and its length that acts as kind of like a threshold.
Okay.
If those competent beds are too short relative to their thickness, you would need way too much flow in the more ductile layers to accommodate the folding. And you probably wouldn't end up with chevron folds. So they kind of need to be relatively long and thin to get that nice chevron shape.
Gotcha. So the layers need to be somewhat extensive and not too chunky, basically, for those sharp, repeated bends to really form. What happens if there are variations or anomalies in the thickness of those competent beds? Like, what if you have a sequence that's generally prone to chevron folding, but there's, like, a weird thick bit in one of the stronger layers?
Yeah, that can lead to some interesting variations in the chevron shape. Like the Wikipedia entry mentions that if a competent bed is unusually thick, you might get these bulbous, rounded hinges developing, or even hinge collapse. Or you might get small little thrust faults popping up within the hinge zone.
Okay.
And on the other hand, if a competent bed is unusually thin, it might undergo something called boudinage, which is where the layer stretches and breaks into these like sausage-like segments. Yeah. Or it might just extend through ductile flow. So even in areas that are generally good for forming chevron folds, these little variations in layer thickness can really throw a wrench in the works and create some local complexities in the fold geometry.
Okay, so we've covered a lot about what chevron folds are, how they form.
Yeah.
But, like, why should we care? Why are these significant to geologists?
Yeah, that's a great question. I think this is where we really connect these interesting shapes to understanding the history of the Earth. Like the YouTube transcript from the Professional Geology Club, they point out that chevron folds act as really valuable indicators of a region's tectonic past.
Okay.
So by studying, which way they're oriented and how tight those folds are, geologists can figure out the direction and intensity of the compressional forces that were acting on the rocks millions of years ago. They're like these frozen records of, ancient squeezing events.
So they're like little clues that tell us about the forces that have shaped the Earth's crust.
Exactly.
That's cool.
And they're also useful for what's called strain analysis. So by carefully measuring the angles and orientations of the different parts of the fold, Geologists can calculate how much shortening, how much squishing those rocks have experienced during the folding process. And that helps us really quantify the scale of past tectonic events.
So it helps us kind of like piece together the history of all that.
Exactly.
Now, the YouTube transcript also mentions something about finding resources.
Yeah, so that's another really important aspect of chevron folds. They can actually be associated with, the formation of ore deposits and hydrocarbon reservoirs, especially in the kind of geological environments where they typically form.
Okay.
So understanding their geometry and distribution can be super valuable for, exploration and extraction of those resources. The folds themselves can create these structures that actually trap those resources, making them easier to find.
Okay, so this isn't just like academically interesting. It's got real-world implications.
Oh, absolutely. And even on a broader scientific level, just understanding the presence and characteristics of chevron folds in a particular geological setting can help geologists build better tectonic models and really, reconstruct the history of an area. By studying these, seemingly small-scale structures, we can gain a much better understanding of the really large-scale processes that have shaped our planet over, millions and millions of years. And the YouTube video even mentions that they've actually observed similar folds on other planets like Mars, which could help us understand their geological evolution too.
Wow, so these are a lot more significant than they might seem at first glance.
They are.
They're like a key to unlocking a lot of things.
Absolutely.
Now, for anyone listening who wants to really get a good visual of these, just do a quick image search online for chevron folds or check out the EGU blogs post. They have some good pictures.
Yeah, seeing them really helps kind of solidify the whole concept.
Okay, so to wrap it all up, chevron folds, with that distinctive V-shape and repeating pattern, they're basically formed when you have compressional forces squeezing rock layers that have big differences in strength or competence. And the way they develop, their final shape, it all depends on a ton of factors, like the initial state of the rock layers, the friction between them as they slide around, and the thickness and length of the individual beds. And importantly, studying these folds gives us valuable insights into, the history of our planet, how much deformation rocks have experienced, and even helps us find natural resources.
That's a great summary.
Thanks.
And, one thing that really strikes me is how sensitive the formation of these chevron folds is to things that, at first glance might seem like really minor variations in the geological conditions.
Wow.
Like, how much of a difference in strength there is between those rife layers, how much friction there is between them, even, those tiny initial imperfections. And it just gets you thinking, what other seemingly small variations in geological conditions might lead to completely different geological structures that we see all over the Earth's crust.
Right.
It really highlights how interconnected all these geological processes are and how these, seemingly small differences can have a huge impact on, the grand scale of Earth's geology.
Yeah, that's a really interesting thought. So much to think about.
There is.
Well, thanks for joining us for this deep dive.
My pleasure.
Until next time.